Hi, this is John Whitaker for the graduate level probability class, and this is our 13th video lecture. And today I want to talk a little bit more about the convolution, where we are interested in the addition of two independent random variables and talk about its probability density function, or even probability mass function will also be discussed about the addition of two independent random variables. We're also going to look at something called the moment generating function, and that's what we'll conclude this lecture with. Okay, so let's go ahead and get started by remembering that fact that we had. So here's the recall. If x and y are two continuous random variables, also independent, random variables, then with the PDF of xb f sub x of x and the PDF of y being f sub y of y, then the PDF of x plus y is f sub x plus y, and then we'll call it a bay. Okay? And this is equal to the interval from minus infinity to infinity of f sub y of y times f sub x of a minus y dy. So that's what we have. And I want to do an example of this next time. Next. So that, recall, was the last thing that we did in video lecture 12, and we proved that as well. So as an example, let us let x and y be two uniformly distributed random variables, let's say independent, uniformly distributed random variables, okay, on 0 to 1 that are independent. And someone might say, fine, f sub x plus y of a, the joint PDF. So here, we'll start off with the solution. And what we'll note is that because they are both uniformly distributed on 0 to 1, and what we have is f of x of, let's say, some dummy variable c. It's the same thing as f sub y, that same dummy variable c. And what's it equal to? It's equal to 1. Remember, it's 1 over b minus a, so that's 1 over 1 minus 0, that's 1 over 1. If c is an element of 0 to 1, and it's 0 otherwise. That's what we have. So, f sub x plus y of a, by our previous fact, what I recalled just a few seconds ago, is equal to the interval from minus infinity to infinity of f of a minus y, f sub x of a minus y, f sub y of y, dy. Now, we're integrating this product between these two functions. And one thing I want to tell you is that we're integrating with respect to y. Now, so this limits of integration with respect to y. The other thing I want to notice is the following, is that f sub y of y is mostly 0. When is it not 0? It's when y is between 0 and 1. So we can go ahead and break this into the interval from 0 to 1 for y values. So f sub x of a minus y, and then f sub y of y is going to be equal to 1 over this region. So that's 1 times this, so I want to write the 1 for f sub y of y. dy, that's what I have. Okay, now let us note something. So first of all, since, well, I think I need a little bit more room. Let me get here. Okay, so what we're saying at this point is that f sub x plus y of a is equal to the integral from 0 to 1 of f sub x of a minus y dy. Now this f sub x is a lot of times 0. The only time it's not 0 is when the input value is between 0 and 1. And so what we need is a minus y has to be between 0 and 1. I'm going to solve for y. This is for f sub x of a minus y to be non-zero, to be equal to 1. So here's what I'm looking at. I'll do this work over here. So what we're looking at here, if I solve for y, is that minus a is less than or equal to minus y is less than or equal to, so I subtract a from both sides. That's what I do. Now I'm going to multiply everything by minus 1 and switch the sign. So I have a is greater than or equal to y, which is greater than or equal to a minus 1. Or we have a minus 1 is less than or equal to y is less than or equal to a. It's the same statement, just written differently. So that's what we have. So y has to be the same between a minus 1 and a. But there's also another thing to notice. Now, since if you will, x values run between where they have a chance of being a value, since x values are between 0 and 1, and, or I should say n, and y, I'll say x, I'll say x is, and y is in, again, 0 to 1, then x plus y is an element of 0 to 2. So what we're thinking is, so a has to be an element from 0 to 2. For it to be non-zero, okay? So we're thinking the a, that's what the a value is going to be. And that's the a value we're interested in for non-zero part. And so here, if I look a little bit more in terms of this a minus 1 being less than y being less than a, and understand how the value of a affects y, here's what I'll do. I'll draw the rectangular coordinate system. Here, where this being the y-axis and this being the a-axis. So here, we have really two equations. We have a minus 1 equals to y, if I think of these inequalities as equations. And that says that y plus 1 is equal to a. Well, let's see, y is supposed to be from 0 to 1. And So when y is 0, a would be 1. And when y is 1, a would be 2. So it's this line. Now, if we look at the other y equal to a line, or a equal to y, it'd start here at 0 and then be up here at 1. We have this line. Now remember, the y values run from 0 to 1, so we're just looking here. This region in between here. And so what we have is these lines split up this region where y can be into different parts. Here, here, and here. Okay? Here, here, and here. But what we're looking for is the y value to be sandwiched between a minus 1 and a. So let us take a look at this particular in our picture so we can see which region we're talking about. The a minus 1 is less than or equal to y is less than a from our picture. Let's notice if we take some point, let's say right here, so 0.5, and then let's take 0.1. So 0.5, 0.1 doesn't satisfy this part of the inequality, so it's not this region. If I take this point, 0.5 and 0.5, then, now we're making 0.5, let's make 0.51. That's in this region here. 0.51, so the y is 0.5, the a is 1. 1 minus 1, 0. 0.5 is bigger than that, and it's less than 1. So this region is included. And if you take some point here, like 0.5, and then maybe 2, okay? So 2 minus 1, that's 1. 1 is not less than 0.5, so it's not that big. So this is the region. So the a values here can, we're thinking they can run from 0 to 2. And what I see is for those particular a values, all the a values between 0 and 2, if you look at what the y values can run from so that it satisfies this quality, for a values in between 0 and 1, the y values will run from here, from 0 to this line. But for a values that are between 1 and 2, the y values run from this line to this line. Those are different values for which the y values can run from. So that's going to create different cases and different intervals for each case that I will be integrating over, so that we make sure that a minus y is some number between 0 and 1. Okay? So here's what we get. You know, on the bottom there of that board, I had said that the a values have to be between 0 and 2. That's true for when the probability would be non-zero. And so that's the part that we're mostly interested in. Here's what I'm going to say. If a is sandwiched between 0 and 1, I'll put equal to it, then our integral, so we're looking at f sub x plus y of a, it's going to be equal to the integral. So as I look back at the picture, the y values need to run from 0 to that line y equal to a, so I'll write down a. And over that region, the a minus y will be in between 0 and 1, over this region from 0 to a, for a values in between 0 and 1. And the a minus y would be between 0 and 1. And so f of x, so f sub x of a minus y dy will really be just the integral from 0 to a of 1 dy, which is just 1, which is just y. We evaluate that from 0 to a, and we just get a. If a is sandwiched in between 1 and 2, then f sub x plus y of a is equal to, so as I look at my picture over there, for A values in between 1 and 2, the Y values, the horizontal line, will run from, it is A minus 1 up to 1. And this will be f of x of A minus y, dy. But that will keep the y values, in the A minus y values in between 0 and 1. So we're really integrating from A minus 1 up to 1 dy. Because this argument right here, for this situation, will be in between 0 and 1, and f of x is something between 0 and 1 is just 0. I'm sorry, it's just 1. So when I integrate this, I get y evaluated from A minus 1 up to 1. So that's 1 minus the quantity A minus 1, which is equal to 2 minus 7. Okay. I'm ready now to write down what the PDF of x plus y is. It's not the joint PDF, it's just the PDF. See my focus. I am. So, f of x plus y of A will be equal to, well, it's 0 if A is less than 0. We found it to be A if 0 is less than A is less than or equal to 1. We found it to be 2 minus A if 1 is less than or equal to A is less than or equal to 2. And we found it to be 0 if A is greater than 2. So that's what our answer is. Well, having done that, I now want to list some facts. Well, I want to list one fact about independent Poisson random variables and their addition. So, if x and y are independent Poisson random variables with parameters. Okay, so for x, the parameter is L sub 1, and for y, it's L sub 2. Then, x plus y is a Poisson random variable. I'll finish that right here. So Poisson random variable with parameter lambda 1 plus lambda 2. Okay, we're going to prove this. Okay, so here's the proof. We're going to let x and y be independent Poisson random variables with parameters lambda 1 and lambda 2. Let f of x plus y denote here's the PMF. So I can't use that fact that I have having to do with the convolution for the sum, the independent random variables, because here we don't have continuous. So x plus y. Then, well, what does f of x plus y of a represent? Well, it's the probability that x plus y equals to a. And what that can be considered as, it could be considered as, if you will, the probability of the union. So here, it's the, I'll say it this way. It is the union, as k runs from 0 to a, of x is going to be equal to k. So x could be 0, x could be 1, x could be all the way to a. But for every time x is a value, for us to get that x plus y is equal to a, then that means that y must be equal to a minus that value for x. So it's y is equal to a minus k. Okay. These are mutually, this event, we're having lots of them, a plus 1 events, and each one of them are mutually exclusive. If k is equal to 0 and y is equal to a minus 0, and then you look at the next event where k is equal to 1 and y is equal to a minus 1, those can't happen simultaneously. They have no intersection. And so when we take the probability of the union of mutually exclusive events, because of the definition of probability, that becomes a sum as k runs from 0 to a of the probability of x equaling to k and y equaling to a minus k. Now the thing to remember is that this comma means and we know that these random variables are independent of each other. So this sum can be rewritten as the sum as k runs from 0 to a of the probability that x equals to k times the probability that y equals to a minus k. All right. Well, the next thing I'm going to do is remember that x is a Poisson random variable and y is a Poisson random variable. So I can compute using the individual PMFs what those probabilities are. At least give a symbolic representation for it. And so what that's equal to is the sum as k runs from 0 to a the probability that x is equal to k. That's nothing more than, so I use the PMF of the Poisson random variable. So it's e to the minus lambda sub 1, lambda sub 1, okay, to the k, all over k factorial. And now the probability that y is equal to a minus k, that's equal to e to the minus lambda sub 2 to the a minus k, all over a minus k factorial. I'm looking at this k factorial and this a minus k factorial, and that looks like the bottom of a combination. But what's the top? So it looks like we should have a. This is almost a choose k, if you will, but it's not quite because we're missing the a factorial. But the index here for the summation is k, and so a is a constant. So what I'm going to do is I'm going to say, well, I can take out the e to the minus lambda sub 1 times e to the minus lambda sub 2. I've got a sum. I'm going to make a little bit more room. A sum as k runs from 0 to a. What I'm thinking is to put a factorial here. And then I have lambda sub 1 to the k, and lambda sub 2 to the a minus k. That's exceptional. All over, and I'm going to concentrate on this, a factorial over a minus k factorial, and then k factorial. Let's don't worry about this term, these multiplications so much. But I've stuck in this a factorial, which I can do because it's a constant, but I have to compensate for it by putting 1 over a factorial up front. So this is equal to e to the minus quantity lambda 1 plus lambda 2, 1 over a factorial. Here, this is a sum as k runs from 0 to a. This part is a choose k. Here I have lambda 1 to the k and lambda sub 2 to the a minus k. And by the binomial theorem, we can apply that. What we get is this is e to the minus lambda 1 plus lambda 2, in parentheses, over a factorial. And the binomial theorem, this matches perfectly to what the binomial theorem would be. And our answer is L sub 1 plus L sub 2 raised to the a. So L sub 1 plus L sub 2 raised to the a. So that is, I'll write it down. So F sub x plus y of a equals to e to the minus lambda sub 1 plus lambda sub 2. Lambda sub 1, so this is not an exponent position of e. Lambda sub 1 plus lambda sub 2 to the a, all over a factorial. Now, that is the PMF of a Poisson distributed random variable with parameters lambda 1 plus lambda 2. Poisson PMF with parameter lambda 1 plus lambda 2. So, this is a conclusionary statement. That's what shows that x plus y x plus y is a Poisson random variable by definition. What do I mean by definition? What does it mean to be Poisson? It has a certain PMF, that type, with parameter lambda 1 plus lambda 2. And that's what we wanted to show. So that ends that proof of that fact. Here are some other facts. I'm going to write them down without proving them. So the first one is, if x and y are independent binomial random variables, with parameters n, or I'll say m and p, that's for x, and n and p for y. So the p's are the same, but the number of trials may differ. Then x plus y is a binomial random variable with parameters m plus n and p. I'm not going to prove that fact, and I've got a second fact that I won't prove. So a similar fact that I'm going to state is that for a normally distributed pair of independent random variables, two, so if x and y are independent normally distributed random variables, with parameters for x, there be mu sub 1 and sigma sub 1 squared, and for y, it's mu sub 2 and sigma sub 2 squared. Then x plus y is normally distributed with parameters m sub 1 plus m sub 2 and sigma sub 1 squared plus sigma sub 2 squared. Okay. We now want to turn to moment generating functions. So this is an important function related to random variables, and here's where it's defined. So we let x be a random variable. Then the moment generating function of x is denoted by, okay, so it's phi, I'm like drawing like this, phi sub x of t, so it's a variable of, it's a function of the variable t, and it's equal to, and given by, phi sub x of t is equal to the expected value of e raised to the tx. Now this is a function, the expected value of the function of the random variable x. So it's e sub tx. That's what we have. Here, let me make a comment. We assume phi sub x of t, the moment generating function, and we'll abbreviate that MGF, the moment generating function, is defined for some interval minus b to b, which contains 0. Okay, I want to list a fact about the moment generating function. So here's a fact. It says that the nth, I just write that, the nth derivative of the moment generating function is equal to the expected value of x to the n times e sub e raised to tx. Expected value of that. It's not hard to prove, so let's do that. So let phi sub x of t, well, yeah, be the moment generating function for random variable x. The proof here is by induction. So let me write that down, by induction. So how do we do this proof by induction? We have to prove the statement is true when n is equal to 1, and then assuming the statement is true when n equals to something arbitrary like k, show from that the statement is true when n equals to k plus 1. So here's the first part. When n equals to 1, the derivative, the first derivative of x to t, equals to the derivative with respect to t of the expected value. Well, I should say this. I should back up. So the first thing I'm going to do is say, when n equals to 1, note phase of x of t is equal to the expected value of e to the tx. So, the first derivative, t, is going to be equal to the derivative with respect to t of this expected value. This is a derivative. Now, a derivative is a limit. Turns out we can bring this limit inside either the sum or the integral, whichever we have here, and it becomes the expected value of the derivative. And now we're taking the derivative with respect to t. So here, this is equal to the expected value. The derivative of e to the something is e to the something times the derivative of the exponent. So we're doing it with respect to t, so that's just x. And that is what we'd like to prove when n is equal to 1. That's exactly right. So the statement is true when n is equal to 1. Okay, now, using induction, we will assume, so this is part 2, assume the statement is true for n equal to k. That is, assume that the kth derivative of phi sub x to t does equal to the expected value of x to the k times e to the tx. We want to show the statement is true for n equal to k plus 1. That is, that phi sub x of k plus 1, the k plus 1 derivative t, is equal to the expected value of x to the k plus 1 times e to the tx. Well, note, phi sub the k plus 1 derivative of the moment generating function value of t, that's equal to the kth derivative of the moment generating function. And I want to take its derivative. Well, that's equal, by the assumption, that's equal to the derivative with respect to t. So maybe that's the way I should write it. The derivative with respect to t of the kth derivative of the moment generating function. Well, that's the derivative with respect to t of the expected value by assumption of x raised to k e to the tx. Again, we can bring the derivative inside the expected value. And because we're taking the derivative with respect to t, x is a constant. So I have to take the derivative of constant times something. Well, you just write down the constant, so it's expected value, it's a constant. And now the derivative of e to the t to the x is e to the t times x, and then I have to take the derivative by the chain rule, t times x, with respect to t, so that's just x. So that's equal to the expected value of x to the k plus 1, e to the tx. And that's what we wanted to show. So by induction, we have the nth derivative of the moment generating function is equal to the expected value of the variable raised to the nth power e times t, e raised to the tx. Okay? And that's what we wanted to show. So that's the proof. A very important consequence in the reason that the moment generating function has its name is about to be written. So here's the fact. Okay, the nth derivative of the moment generating function evaluated to 0 is equal to the expected value of x raised to the nth power. So the expected value of x raised to the nth power is called the nth moment. So I'll just write this to the side. It's called the nth moment of x. Okay? And so this function generates the moments, and that's why it's called the moment generating function for the random variable x. Okay, let's look at the proof of this. Well, the nth derivative of x of t, okay, evaluated to 0. That's what this is. So I'll just put the 0 here. Is the same thing, I'll symbolize it, as the nth derivative of the moment generating function of t to be evaluated as well at 0. But I have just proven in the previous fact that this is the expected value of x to the n e sub tx evaluated when t is equal to 0. So here when we let t be equal to 0, this is equal to the expected value of x raised to the n e to the 0 times x. And of course 0 times x is 0, e to that is 1, so that's equal to the expected value of x to the n. And that's what we were trying to prove. Now we're going to use that to find the moment generating function. Well, we'll find the moment generating function for some famous random variable types, and then use the fact that we just did to find the expected value and the variance using the moment generating function. Okay. So here's the fact. So we'll, if x is a binomial random variable, with parameters let's say n and p, then the moment generating function of x is phi sub x of t, and it's equal to, so it's p times e raised to t plus 1 minus p all raised to the n. That's what it is. And so we want to prove this. Well, okay, so to prove this, we say let x be a binomial random variable with parameters n and p. Okay, and we're trying to show that this is the moment generated function. Okay. All right, so I think I'm in focus. So, phi sub x of t, well, what's it defined to be? It's defined to be the expected value of e raised to the tx. Okay? And we're talking about a binomial random variable. So what is this? This is the sum over all the output values you have for x. So x can run from 0 to n. And then it was e raised to the tx, that's the function, and then it should be f of x, that's what the sum is. And I've already said the x value runs from 0 to n. So this is equal to sum as x runs from 0 to n, e raised to the tx. What was the probability mass function for a binomial? Well, it's n choose x, p to the x, 1 minus p to the n minus x. That's what we have. Okay, what I'm going to do is I'm going to rewrite this sum is that I'm going to say, well, we have e to the t raised to x and we have p raised to x, so I'm going to combine them. So this is n choose x, e to the t times p, all raised to the x, times 1 minus p to the n minus x. Okay. Now, as I look at this, again applying the binomial theorem, which this fits perfectly, then what I get is it's this guy plus that guy raised to the n, and that's what the answer is supposed to be. So I wrote it down this way. P times e raised to the t plus 1 minus p, all of that raised to the n. That's what we're trying to show. Okay, let us verify what the expected value is and what the variance is. Okay, look, I know what the expected value of a binomial random variable with parameters n and p are. It's n times p. I know what the variance is. It's n times p times 1 minus p. We're going to verify that using the moment generating function, okay, and taking its derivatives and evaluating it 0. So, okay, so note, the expected value of x will be equal to phi sub x prime evaluated 0. Now, phi sub x of t, what was that? That was p times e raised to the t plus 1 minus p raised to the n. So what's the derivative? So I'm taking the derivative with respect to t. This is my function, it's raised to a power. How do you take the derivative of something raised to a number? Well, that is, you write down the number, so it's n, times the something, raised to 1 less power. Now I'm going to take the derivative by the chain rule of what was being raised to the power. Now remember, we're taking the derivative with respect to t. So here, I see a sum. The derivative of the sum is the derivative of the first guy, which would be p times e to the t, plus the derivative of the second guy. But the derivative of the second guy, that's a constant with respect to t, so that's just 0. So, when I take this derivative of this function and evaluate it to 0, so I'm evaluating t is 0. So it's n times p to the e raised to 0 plus 1 minus p raised to n minus 1 times p times e raised to 0. Okay, so this is equal to n here, this is p minus p, that's just 1, 1 to the n minus 1 is just 1, and this is p again times 1, so this equals to np, and that's what we were hoping to get. And so the expected value of x is equal to np. We already knew that was the answer, but this is just an example of we can get the expected value using the moment generating function. Okay, well, let's talk about the variance. So, note the variance of x is equal to the expected value by formula of x squared minus the expected value of x. I already just found this. That was n times p. So we need this. The expected value of x squared by our previous fact is equal to the second derivative of the moment generating function evaluated at 0. Well, let's recall, so since, I mean look, since phi sub x of t prime was equal to, so I'm going to look over here, I already calculated this. It was n times p times e to the t plus 1 minus p raised to n minus 1 times p to the et times p times e to the t. Then, the second derivative, okay, so overall what I see is something times something, so I'm going to have to use the product rule to take this through. So I'm going to write down the first thing. Now I take the derivative of the second. The derivative of the second is itself. Plus, now I write down the second. Now I take the derivative of the first. The derivative of the first guy is n, and then to take the derivative of something raised to the power, it would be times n minus 1 times p e raised to t plus 1 minus p raised to 1 less power would be n minus 2. And then you have to multiply by the derivative inside. The derivative of the inside by the chain rule is the derivative of p raised to the et, but that's just p raised to the et, so I'm going to square this part. And that's what I get. So if you take this the second derivative of the moment generating function and evaluate it at 0, what we get is we get n times, well, p e to the 0 is just 1, plus 1 minus p to the n minus 1. Here, this is p times e to the 0, that's just p. And then plus, here, this is going to be p times e to the 0, that's just p, but I got to square it. Here, this is n times n minus 1. Again, when I let t be 0, this is p plus 1 minus p raised to the n minus 2. So, what is this? This is n, this is 1 to the n, that's just np, that's what that is. And here, this is plus p squared n times n minus 1. And again, this is 1 raised to the power n, so that's what we get. But that's just the expected value of x squared. I haven't got the variance yet. Remember, I know what the variance for a binomial is. It's n times p times 1 minus p. We've shown that previously. So, the variance of x equals the expected value of x squared minus the expected value of x to b squared. You know what? I didn't write this right. I'm sure if you were in the class here, you'd have said, ha, you forgot something. So by formula, it's the expected value, the variance is the expected value of x squared minus the expected value of x to b squared. I'm sorry, I made a mistake. Make that change. Okay, so I rewrote it there. And so that's equal to, we just found this part, I'm looking at it, it's n times p plus p squared times n minus 1 minus, this is np, so it'll be n squared p squared. Okay, so what is this? This is np. Here, this is p squared n squared is plus, and then it's a minus p squared n, and then it's a minus n squared p squared. So these two guys cancel with each other, and we're just left with n times p minus p squared times n. If we factor out a pn, or np, then this becomes 1 minus, I've taken out a p, so I've got a p, and I've already taken out the n, so that's all that's left, and that's what we were hoping to get. Okay. Well, here's another fact. If x is a Poisson random variable, with parameter lambda, then the moment generating function f sub x of t is going to be equal to, so here's the answer, it's e to the lambda, so the power is lambda times e to the t minus 1. That's what it is. So it's e raised to the quantity, lambda times the quantity e to the t minus 1. Okay, so this is the power. Let's prove that. We're going to prove it using the definition of the moment generating function. Okay, so prove we let x be a Poisson random variable with parameter lambda. Then phi sub x of t, by definition, is the expected value of e raised to tx. Now this is a discrete random variable, so it's a sum. And here, over the x values of e raised to tx times f of x. So now I've got to remember all of this. What does the x values run from? They run from 0 to infinity. Here, this is e, t, this shouldn't have been a big x, it should have been a little x. E raised to tx, alpha of x, what was that? It was e to the minus lambda, remember it's got parameter lambda, lambda to the x all over x factorial. Okay, the e to the minus lambda doesn't depend on x, so it can be taken out. Sum as x runs from 0 to infinity. And then what we're left with is, I'll regroup this as lambda times e to the t all raised to the x all over x factorial. Now Taylor's theorem tells me what this is. So this is e to the minus lambda times e, and it's lambda times e to the t. So that's what that is by Taylor's theorem. So this is by Taylor's theorem. And now I can add these, so it's in terms of power. So it's e to the minus lambda plus lambda times e to the t. I can take out a lambda as a factor in the exponent, so it's lambda times, and I'll write this first, it's e to the t and then minus 1. And that's what we were trying to prove. Okay, let's verify using the moment generating function, what the expected value of Poisson would be and what the variance would be. Both of them are lambda, but let's verify that. And that'll be the last thing we do for this video. note, the expected value of x is nothing more than the first derivative of the moment generated function evaluated at 0. So phi sub x t, we've already found that. I'm looking at e to the lambda times the quantity e to the t minus 1. So the derivative, okay, this is e to something. How do I take the derivative of something? E to something. It's e to the something times the derivative of something with respect to t. So here I've got to take the derivative of this. So it's times. This is going to be lambda. That's a constant, and I've got to take the derivative of this, but that's just e to t. And so phi sub x prime evaluated at 0, that's e lambda e to the 0 minus 1 times lambda e to the 0. E to the 0 is 1. 1 minus 1 is 0. 0 times lambda is 0. E to the 0 is 1. Here's lambda. This is 1, which just equals to lambda. And that's what we said it's going to be. Okay? And so, note, the expected value of x squared is equal to the second derivative of the moment generated function evaluated at 0. Now, the first derivative of x evaluated at t, I've already got that. That's e, right here it is, the lambda e to the t minus 1 times lambda e to the t. And so, the second derivative of the moment generating function evaluated at t. So here, this is, I have something times something else, and I need to use the product rule to take its derivative. So I'll write down the first times the derivative of second. The derivative of second is just lambda e to the t. Plus, I'll write down the second, lambda e to the t. I take the derivative first, but that's e to the something times the derivative of something, which is lambda times e to t, so this guy's squared. Okay. We're almost done. So, phi double prime evaluated at 0. I need to look here. This would be e raised to the lambda times e to the 0 minus 1 times lambda e to the 0 plus lambda times e to the 0 to b squared. And here it's e to the lambda times e to the 0 minus 1. Okay, e to the 0 is 1, 1 minus 1, 0. This is 1. This is lambda, so that first part's just lambda. Plus, this is 1, 1 times lambda is lambda, lambda squared. And then this is 0, e to the 0 is 1, so that's what we get. So the variance of x for this Poisson random variable is nothing more than the expected value of x squared minus, I'm not using the formula this time, expected value of x to b squared. We just found this to be lambda squared plus lambda, I got it, minus, this is lambda to b squared, and so we again get lambda. That's what we wanted to show. Thank you very much for your time and patience.